Hello. So this section is about still confidence intervals for the population mean. But now what we are going to be talking about is what if we don't know sigma? What if sigma is unknown? So previously we talked about in all the problems in the previous section, we know the population standard deviation. So remember, sigma is the population standard deviation. But what if we don't know the population standard deviation? What if we just have our sample? And this is actually what happens typically. So I wouldn't call the previous section useless, but because it kind of this builds on the same concepts as what we just talked about. So I don't think you'll find this section particularly difficult. In fact, because of this section, you'll probably find the previous section even easier. But what I am going to emphasize is basically in real life, we don't know the population standard deviation. We're going to use the sample standard deviation. And the sample standard deviation uses something called, if we know the sample standard deviation, we have to use something called the t-distribution. And to calculate a t-statistic, it's x bar minus mu over s over the square root of n. And to kind of give you, remember z-score is x bar minus mu sub x bar over sigma over the square root of n, because sigma over the square root of n is sigma sub x bar. But now, basically, these are the same thing. In fact, we can put an x bar here if it makes you feel better, because mu and mu sub x bar are equal to each other. But what is different? Well, now we have a sample standard deviation, right? The only thing that is different is that we substituted sigma for s. And this follows a t-distribution. Okay, so let's talk a little bit about the t-distribution, and then I'll talk more about when it's actually used. So the t-distribution is very similar to a normal distribution. It's bell-shaped and it's symmetric about the mean, but probably the most distinguished feature is that a t-distribution is actually a family of curves, and it's determined by a parameter called the degrees of freedom that uses a formula that you must memorize. And the formula is the degrees of freedom is equal to the sample size n minus 1, and that's it. Isn't that nice? Yeah. But that's basically the most distinguished feature. The total area under the curve is 1 or 100% because it is a probability distribution. The mean, median, mode of a t-distribution are equal to 0. And 5, and this is another interesting part, that as degrees of freedom increase, the t-distribution approaches a normal distribution. This always happens. And after about 30 degrees of freedom, which means it's what our central limit theorem says, the t-distribution is very close to a standard normal distribution. Well, what does this mean? So let me show you. So let's say we have a low number of degrees of freedom. So all t-distributions are relatively, or they are all symmetric. But if you have a low number of degrees of freedom, your curve isn't as high. So if this is like 2 degrees of freedom, there's a lot of area in the tails, and there's not as much area in the center. But as my degrees of freedom increase, I get more area in the center and less area in the tails, until finally I have an almost perfect bell curve. So this might be, I don't know, 5 degrees of freedom, and then finally after about 30 degrees of freedom, you're at a almost perfect normal distribution. And if you want, you can go to your book and look in your book. There's a better picture of this in section 6.2. All right, so basically we've been talking about this margin of error formula where the z-score we use the z-score times sigma over the square root of n. But because now we know the sample standard deviation, we still have to calculate the margin of error, and everything is the same. The only difference is instead of a z-score, we have to find a t-score, and instead of sigma, it's an s, because that's still standard deviation. It's just a sample standard deviation. And the n is still sample size, so we still divide by the square root of n in both formulas. So basically, how do we know when to use what? Well, if n is greater than or equal to 30, or the population is normally distributed, if you can answer yes to either, okay, then you can move on. But if you answer no to both, and I'll put in parentheses to both, no to both, then we can't create a confidence interval. And I'll put a frowny face because that's sad, right? So if you don't have a large enough sample size and the problem doesn't say the population is normally distributed, then you can't create a confidence interval. But let's say either of those are true, then we look for this. We look for sigma. Now remember, sigma, they have to give you a standard deviation, and I can't emphasize this enough. We're looking for the word population, basically. Is there a population standard deviation? If it doesn't have the word population or has the word sample, then it's going to be a sample standard deviation. They pretty much have to say the word population for it to be a population standard deviation. So if it is a population standard deviation, that's what we've always done. That's the z-score times sigma over the square root of n. And if it's not a population standard deviation, that's a t-score times s over the square root of n. Okay, so on the next page, I'll write normal and t here really fast. Okay, so on the next page, there are 4 scenarios, and we're not going to construct confidence intervals yet, but all I want you to do is just read through the 4 scenarios, and I want you to tell me, are you using a normal distribution, are you using a t-distribution, or is it an either? Can you not create either? Can you not create a probability or a confidence interval? Can you not create a confidence interval? So read through the 4 scenarios, pause the video, and look at what I come up with. Alright, so hopefully you did these on your own. So the first thing we look for is our sample size large enough, or is the population normally distributed? And we have 25 newly constructed houses, so our sample size is less than 30. However, it does say we can't assume they're normally distributed, so we can move on. So we're moving on, and then we say, do we know the population standard deviation? Well, yes, we do. So this is a normal distribution. Okay, next one. In a random sample of 70 bolts, the mean length was 1.25 inches and the standard deviation was 0.05 inch. So I'm looking at this and I say, okay, is my sample size greater than 30? Yes. Is it normally distributed? Well, it doesn't say it's normally distributed, so no, I can't assume it's normally distributed, but that's okay because I have 70 bolts, because you only need one or the other. So my sample size is good. Do I have a population standard deviation? I have a standard deviation, but it's not a population standard deviation. So therefore, this is a t-distribution. All right, this one, 19 patients at the hospital, so my sample size is not large enough, and it's actually not normally distributed either, so this one's a neither. So that's a frowny face because we won't be able to create a confidence interval. Now, by the way, this last sentence is kind of a courtesy. If it doesn't say that the waiting times are normally distributed, even if this specifically says they're not, but even if it didn't say they're not, you can't assume they are. So you should still say neither, even if the last sentence wasn't here, because you can't assume those things. It has to tell you. And the last one, we have 12 2-slice toasters, so that's not a large enough sample size, but the prices are normally distributed. Okay, so we're good there. Do we have a sample standard deviation? Well, it looks like from the sample we got the standard deviation. So yeah, this is a t-distribution. And I find this one interesting because a lot of people want to say they see normally distributed and we're like, oh, we're going to use a normal distribution. Normally distributed does not mean you are using or a normal distribution. It just means that you're able to create the confidence interval. What determines the difference between normal and t is that t is a sample standard deviation and normal is a population standard deviation. So make sure, because you're kind of using the same terminology for both, but make sure you use the t-distribution if you know a sample standard deviation. All right, and these are the four. So it was normal, t, neither, t. All right, so let's actually do a few examples of this. And I'm going to post the reference sheet for the normal distribution chart and the t-distribution chart. But I'm going to teach you how to use the t-distribution chart first. So before, when we found a z-score, you had to find the area under the curve, and it took a little bit of time. But for t-distribution, it's actually easier. So all we need is the 95% confidence level, and we want a sample size of 15. Well, if you recall, the degrees of freedom is that fancy formula we came up with in the beginning, which was n minus 1. So my degrees of freedom, n, is 15. So I'm looking for the t-score for 95% and 14 degrees of freedom. Well, if you look at the reference sheet, this is the same reference sheet I will give you. And there's several reference sheets here, so you will have to scroll down a little bit. But it's the fifth one. It has a t at the top. Okay? And don't ignore tail probability. We're not going to really talk about tail probability in this class. But we are going to look at the left side. So the left side is degrees of freedom. And if we go back, our degrees of freedom was 14, and our confidence level was 95%. So 14, we want to look at this row. And if I go down, I see confidence level. Well, confidence level 95%, so then I'll go all the way, follow this 95% all the way up to 14, which is 2.145, and that's how we find a t-score. We just have to look it up in the chart, which is pretty nice. By the way, this is a cool tip. Something the reference chart shows you is z-scores. This whole last row are z-scores, because as degrees of freedom approach infinity, and that's a little infinity symbol there, you are at a normal distribution. So what's the z-score for 95%? You should remember it's 1.96. And look, this is 1.96. If you go back, what's the z-score for 90%? 1.645. What's the z-score for 99%? 2.576. I think we used 2.575. 2.576 is actually more accurate. But notice those are all z-scores at the very bottom. So if you have a popular confidence level that's used, like 50, 60, 70, 80, 90, 95, 96, 98, 99, and so on, all these, you can use this chart for z-scores as well, even though it's the t-distribution chart, because it's on the infinity line for the degrees of freedom. Now, something to keep in mind, like if I ask you to find the z-score for 96% confidence, actually 96 is on here, so let's say it's 97% confidence, 97 is not on the chart, so you're going to have to actually figure out that z-score. But otherwise, yeah, that's how you find the t-distribution. So let's actually go through a couple full examples using a t-distribution. So let's talk about coffee. So we randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162.0 degrees Fahrenheit with the sample standard deviation at 10.0. Find the 95% confidence interval for the mean temperature And we can assume the temperatures are approximately normally distributed. So even though we only have 16 coffee shops, we have the approximate normal distribution, so that's our go ahead. And the same 3 steps as we did in the previous section to create the confidence interval are the same as the same 3 steps here. So if you remember, the first step is the point estimate, which is x bar. Well, what's x bar? It says the sample mean is 162 degrees Fahrenheit. All right, margin of error. So now we have to make a decision. Is this a t or a z? Well, do we have a sample or a population standard deviation? They tell us specifically it is a sample standard deviation, so therefore we're going to use a t-score times s over the square root of n. Okay, well, what's our t-score? Well, first, we have to get our degrees of freedom. We have 16 coffee shops, so degrees of freedom is based off this 16. 16 minus 1 actually, which is 15. So we want, with 15 degrees of freedom, what's our t-score for 95% confidence? So we can go to our chart, 95% confidence, 15 degrees of freedom is 2.131. It's right here. Okay? And that's it. So nice that we just have a chart that we can look it up in. S is our standard deviation, which is 10. And n is the square root of 16. And we get a margin of error of 5.3. And I'm just using 1 decimal place again because I'm matching what the mean is. Finally, we add and subtract the margin of error from x bar. And that's it. So when I subtract, I get 156.7, and when I add, I get 167.3. All right, so really the only difference in the steps is this t-score, right? This t-score is different because we have a sample standard deviation, and we're using 2.131 again because we looked that up in the chart with the 95% confidence in the 15 degrees of freedom. So our sentence is 95% confidence, population mean coffee temperature is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Okay, so try to do the same method, but on the next one. And the next one's about mortgage rates and percentages. Some people try to change the percentages to decimals. Don't do that. Just keep them as the percentages. So hopefully you tried the last one on your own. And let's do this. So it says you randomly select 20 mortgage institutions. So once again, we don't mean the sample size requirement, but it says approximately normal, so we're good. So x bar, our average is 6.22. Margin of error. So for the t-score, it's 99% confidence this time, and our degrees of freedom is 19 because our sample size is 20. Don't forget to subtract that 1. So if you look at 19 degrees of freedom and 99% confidence, 2.861 is the t-score. It's right here. Standard deviation is 0.42. Square root of 20. And my margin of error is 0.27. Notice that now my margin of error, I'm going to put 2 decimal places because my mean and standard deviation were both 2 decimal places. And then we add and subtract the margin of error from x bar. So when we subtract, we get 5.95 and 6.49. So, as always, we'll write the sentence, 99% confidence. The population mean mortgage interest rate is between 5.95% and 6.49%. And that's it. All right, so that is t-distributions using a normal distribution, or using using the t-distributions but creating confidence intervals for the population mean. One final thing I want to say is I will not tell you, this is a normal distribution problem, this is a t-distribution problem. Make sure you know this flowchart and when to use what. Okay, specifically, you need to know when to use a sample standard deviation. That's a t-distribution, and a population standard deviation, that is a normal distribution. So make sure you know what situation you're in at what time. All right, and that's section 6.2. We only have one more section in chapter 6 that we're going to talk about.